Okay, so here we have DSP101 Lecture 2. Woo! There you go. I think there's some new faces. Who here wasn't here for the first one? You weren't. Did you happen to watch the video or? Oh, nice. Okay, cool. Wow, very proactive. So, yeah. So without further ado, let's just begin. So last time we talked about the basics of communication. We talked about DSP basics in the sense of sampling. We talked about the Nyquist sampling theorem. We talked a bit about amplitude modulation too. So we touched on those kind of basic concepts. But today we're going to move on to digital communications. This is going to be probably the most useful stuff that you'll learn. Like the bulk of what you'll do on the DSP team is all digital communications. Everything nowadays is digital. So yeah, this will be a lot more like useful, but it builds on what we talked about before. So also, final note, this is going to be like a multi-part series for the digital stuff. So this is the intro today. Low-key, I'm finding making these is like helping me learn a lot, which is super cool. But yeah, we'll do like next time we'll do a more niche topic called pulse shaping, and then we'll do another one after that, and then we'll cover all the digital stuff. So let's begin. So we touched on before analog modulation, amplitude modulation in particular. And we mentioned that if you want to communicate from A to B, the way that we do it nowadays is with modulation, which is the process of varying a wave in some predictable way to encode information. So I'll repeat, the way we communicate is using modulation. So now we're talking about digital communication. So what is the point? Why are we shifting this gear from analog to digital? What is the benefit? What's the point, right? So digital communications is different in one way, and it's that if you look at it at a high level, it's different in one way, and that's what you're sending. So analog modulation, analog communication, I should say, you're sending an analog waveform. So that could be like speech, like you're talking to a microphone, and it's a varying sound wave. It could be you want to send a certain frequency, like a note on a music, like in the first project. Digital, you're sending bits. You're sending digital, basically discrete information. So 1, 0, 1, like basically that's the main difference. And just that difference alone is huge because it changes the way that we build the entire system, right? Okay, so digital communications is concerned with sending discrete information across a physical channel. And the key here is that the air only works with continuous waveforms, right? Like you can't have infinite jumps. It's all like slowly varying, continuous. You know, there's no like everything. You can't have infinite jumps basically, like from 2 to 4 instantly. It's not possible. You have to go gradually from 2 to 4. So it's always continuous in the real world. Yep. So nearly all modern communication, from phone calls, Wi-Fi, satellite links, internet, all digital. So that's the motivation for you to learn this concept. So I mentioned digital in digital communications refers to the nature of the information, not the waveform itself. Okay, the waveform that you transmit over the air is always continuous. It's always analog in a sense, right? But the difference is the information source, right? So, yeah, this is what we learned last time, that communication is accomplished via modulation, where we encode information by varying properties of a carrier signal. So that's a bit of an intro for you. I haven't really said a whole lot. I've just kind of set up the scope of what we're talking about today. So the question now is, so how do you do digital communication? How do you encode ones and zeros into a continuous carrier signal? And we will see that now. So as I mentioned, the way we do communications is with modulation. So it probably follows pretty logically that the way you do digital communications is with digital modulation, right? So I will take your attention immediately to this diagram here, because I just said a lot of words, so I know we like diagrams. So if you look at this one, you can see the first and simplest way that you can do digital communication, and this is called on-off keying, okay? So the basic idea is you've got your bits, your ones and zeros, and you have your continuous cosine wave, and all you do is you turn it on and off. It's literally just clicking the power button, and that is called on-off keying, and that is the simplest way of modulating or doing digital modulation, and hence accomplishing digital communication. So I'm saying this is the bits only way. You'll see what I mean in a second, but I'm just saying that we're going from bits directly to the modulated waveform. Yep, so one way you could do this is doing ones and zeros on and off keying it's called. And yeah, okay, so what do we notice? First of all, this is last time. This is our amplitude modulation scenario. So we've got our message, our carrier, and we're modulating the carrier with the message. And you can see the envelope contains the message signal. What do we notice, first of all, is that it seems to be like you've got like a 1 and then it's an interval. And then 0 is like a separate interval. Like it's more of in digital communications, you've got these fixed time slots. And during that time slot, the 1 occupies the whole thing. Like, for example, here, there's no time slots. It's continuous. Like every point on the message signal is represented in every point in the transmitted signal. But here, there's these time slots, and that's really important. So we'll revisit that later, but that'll be absolutely crucial. So then we've got this idea of symbols. And this might be a term you've heard if you've studied digital communications. If not, that's completely fine. But the key here is to note that with on-off keying, we are transmitting 1 bit in each time interval. Let me show you what I mean. So consider this to be a time interval from this rise to this rise. And during this interval, we're only transmitting a 1, right? Okay, but that's fine. But the question is, can we do better? Can we transmit 2 bits in a single interval for the same fixed interval time? Well, the answer is yes. And actually, you can go even more than that. You can go 3 bits in the same interval, 4 bits, and that's what we do in real life. If you ever note, here's a cool example for you. Your phone, sometimes you might notice, like, why does the Wi-Fi speed get slow? And why is it fast when I'm close to the router and then slow when I'm far away from the router? That is your phone changing modulation scheme from one that has lots of bits over the same interval to less bits, in the sense that when you're close to your router, the signal is strong, so your phone can decipher between lots of different heights. So it goes lots of bits for the same interval, so it's lots of data. It's really fast speed. But when you go far from your router, it can barely tell the difference between 2 heights, so it goes to a lower modulation scheme. So it's like on-off keying, right? On-off keying, and that's very slow, so your Wi-Fi speed slows down. Yeah, so this is the idea of symbols. So what we do is, this is a term that we came up with. It's what you take your bits, you map them to something called a symbol, and a symbol represents basically what you're encoding into the wave. So you could say here that a symbol is a height. So we got 0, 0 as our bit pattern, and that maps to this height, and that's our symbol. And then 1, 1 maps to this site. This could be height of 4, so the symbol is 4. Here it's 2, 3, so on and so forth, right? Yeah, that's the idea of symbols. And the benefit of this, again, is to increase our bit rate. So over the same interval of time, you now have more bits, so faster speed. Great. We'll see why there's a downside to this later on. I can touch on it with the example of the Wi-Fi speed and stuff. Yeah, it's got pros and cons. So how do we map bits to symbols? This is called symbol mapping, of course. And there's many different ways you can do this. So here's a simple example on the right, where A is an amplitude of our cosine wave. And I'm showing you that you can map bits to different heights. So this is symbol 3, symbol 2, symbol 1, symbol 0. And the pattern 0, 0 is mapped to a height of 3. Let's say A is this 1. So it's 3, 1, minus 1, minus 3. And then what you can do then is, if you want to send your data, you could just have your cosine wave, and height of 3 over that interval means 0, 0. Next interval, height of minus 1 means 1, 0. So you can see how you can transmit your digital information. This diagram here is very important, very important. Not the specific pattern, but the diagram axes. It's called a constellation diagram. If you look up digital communications, you will see diagrams like this with these circles on them, and the axes are often I and Q. Constellation diagrams are very important. Think of them like a star, like a constellation of stars. That's why they're called that. But what they're showing is, they're showing you the modulation scheme. This one also shows the mapping, the symbol mapping. So it's showing you that this symbol, which is what the circles are representing, is 0, 0, 1. This symbol is 0, 1, 0. That's the first thing it shows, but not all these constellation diagrams show the symbol mapping. Often you'll just have the circles with no bits labeled next to them. But the modulation scheme it's showing here, well, I'll touch on what the I and Q mean later. Don't worry about that for now. But just note that this one's a bit of a weird one, actually. I'll explain what the one for this would look like. You know what? Let me show you. Let me show you. What do I have? Let's go share this tab instead. MSA modulation. And then let's go constellation diagram. Oh my gosh. Okay. Yeah, here we go. Look at this. So this is going to be a one-axis constellation diagram. The reason is, I'll touch on it in a bit, but it's because of phase. So the one I showed you, you're only changing the height of the cosine, right? You know, 3, height of 3, height of 1, height of -1, and -3. So this is what this is showing here with the different heights. So this is height of 0 is this symbol, this height is symbol 1, this height is symbol 2, and so on and so forth. This is called MASK, or that's the term for it. You'll pick these up as you get more familiar with the space. M meaning like multiple, like here M would be 4. It's the general term for it. And ASK meaning amplitude shift keying, which is another way of like saying you're changing the amplitude of the carrier. Anyway, that's the constellation diagram for that example. And this one we'll see later, but the point is that in this, well, on the right, I show you can change the amplitude, but you can also change the phase, which is what this one at the bottom does. Okay, so it turns out we had some technical difficulties. I accidentally ended the recording halfway through during the lecture in person. So I'll be giving the second half of this lecture online at home, you know, just for future reference. And I think it's good to finish the full lecture. So without further ado, let's begin. So we just finished off on the digital modulation overview. So we just covered you know, the idea, you got bits to the signal, you've got on-off keying, and you've got what are symbols. You know, we touched on basically the introduction to why we consider symbols. The idea here that you can pack more bits into the same fixed time interval, then symbol mapping, and then digital modulation, 2 viewpoints. So this is a very important, this is more of a framework, I guess you could say, for navigating and learning about the space that is digital modulation. I think this is something that people don't really explain. I came up with it on my own after browsing the space and spending a few years learning this now, only 2 years, counts as a few. So what I'm saying here is there's 2 ways to look at digital modulation, and one is helpful in a certain context and harmful in another, because it will get you confused, and the other is helpful in a different context and like also harmful in a different context. So what are these viewpoints? So they are the polar form viewpoint, I call it, and the rectangular form viewpoint. So what am I talking about? So let's remind ourselves of the situation here. So it's that we have in digital modulation, we have our symbols, and they can be complex values. Let's say you have a complex number on the complex plane, and that is going to get mapped to a discrete carrier state. And like, for example, amplitude of 3A or amplitude of -A, or a phase of, you know, 45 degrees or whatever that encodes that information, right? So the problem here is that, well, if we remind ourselves of math from before, hopefully you guys are familiar, is that with complex numbers, they can exist in both a rectangular form and a polar form. So when you think of symbols, which are complex numbers, which form should you use? Right? This is where you have the divide of the polar and rectangular ways of looking at modulation, because these symbols are, you know, core to modulation. So polar form, let's remind ourselves, we have amplitude and we have a phase. If you follow my cursor here, you have amplitude and a phase. Phase being the angle from the positive real axis, and the magnitude here being the, you know, straight line distance from the origin. That is the polar form. Rectangular form is if you write them in terms of the you know, lateral distances, straight line distances of the axes. So for example, here you have 3 and 4. So this would be 3. I'm not going to turn right, it's going to go away, but 3 plus 4j is what this complex number would be in rectangular form. So what I want you to just accept for the time being, and I'll explain and show why later, is that polar form is very helpful for a high level theoretical, conceptual, well, lots of terms there. Let me start over. It's helpful for a high level theoretical understanding of digital modulation. So if you're thinking about the system as like in a textbook sense, like what does it do? You know, what if you're learning about it, that's when it's useful. Rectangular form is more about the practical implementation. And this is also important when learning about it, if you want to implement the system or, you know, learn about how they're implemented. But what I'm trying to say is that there are different levels of abstraction. So the polar form is very helpful at a high level abstraction. And as you go down lower to the real implementation, you want to switch over to rectangular form. And let me show you why. So first of all, polar form. This is the high level of abstraction level. So let's say we have our carrier here being a cosine, and we have our symbol. Let's say it's in polar form, right? So it's two with an angle of 30 degrees. And what this actually means is it can be thought very directly. This is why I say polar form is useful, in the sense that what it does here is it sets the carrier, the cosine, to amplitude of 2 and a phase of 30. That's easy. The numbers are both there. Like literally all it's doing is you have 2 times the cosine, blah, 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 and the angle is 30 degrees. And that's literally, it tells you everything it's doing. That's why it's so helpful, because it tells you what it's going to do to the carrier. Easy. So we have amplitude and phase modulation. Next example, same idea here, unit amplitude. So it's going to set it to 1, then have a 120-degree phase shift. So if you think about symbols in polar form, they are so easy. And this will come back to be relevant when we talk about modulation schemes. For example, there's one where you have 4, it's called QPSK, if you've heard of it. Not, that's fine. And all it's doing is you have 4 different phases, and those are your symbols. So what you're doing is you're taking your carrier and you're encoding information into it by adjusting its phase to 4 possible options. The amplitude is set to a fixed values. The amplitude of your cosine never changes, but all that changes is the advancement of the cosine in each interval. And in that case, you just have, like in symbol 2 at the bottom here, 1, and then the angle, and then you have, what you're saying the cosine to. So it's really simple in polar form. Here is the limitation of polar form. I mentioned that it's helpful at a high level of abstraction, but as you go down to the implementation, polar form isn't helpful anymore. And that's because if you think about what I just told you, that you have a symbol, and what's happening at a high level is you have amplitude modulation of the carrier and phase modulation of the carrier. That implies that the hardware consists of a phase modulator and an amplitude modulator in cascade. Here I put the phase first, doesn't matter, but it could be either one in front. But the point is, it implies that you have a phase modulator and an amplitude modulator. That's not what happens in practice. That is not what the hardware is for a digital modulation system. That is not true. And the reason is because a phase modulator is tricky to make. Like, we'd prefer not to. I don't know a whole lot about the making of phase modulators and stuff. It's not an area I'm too familiar with, but from what I've seen, it's not an easy, trivial task. They're tricky to make, and we just don't like them. We don't like phase modulators, so we want to stay away from those. And this is not what we do. This is not the reality. So let's talk about what actually happens at a hardware level. And this is rectangular form. So I wrote here at the top the implementer view, right? So let's remind ourselves rectangular coordinates mean you have your symbol, then you have your I and your Q, which is just notations that we use in digital communications for like the axes. I think you could write A plus JB or whatever, right? We use I and Q as the 2 values. This is just showing how you convert. Don't worry about that. So it's emphasizing that they're equivalent representations, but I'm sure that's obvious. So what do we have here? So we have our symbols in rectangular form, I plus JQ, and then we have our carrier. And somehow we have to encode this symbol onto this carrier. So let's take an example of you have a symbol. Let's say it's 3 plus 4J. Is that obvious to you how 3 plus 4J is represented on a cosine? Not obvious. If you have a magnitude of 2 and a phase of 30, well, you set the amplitude of the cosine to 2 and the phase to 30, easy. But in rectangular coordinates, it's not obvious, to me at least, how you would map that I and Q to the carrier. And that's the point. Like, that's why the polar form is useful at a high level, but this isn't useful for that. But let's see how that actually would happen. So to answer that question, you need some trig identities. You need to use some math. And here I have the derivation. So here we have our carrier here, and what I've shown is the polar form. I'm starting with polar form because we're familiar with that one. And here I'm showing that, okay, you have your A and your phi for your symbol. And say it's in polar form. So those are the 2 characteristic parts. Then you're going to use some trig identities. You're going to rearrange, blah, blah, blah. You can look at the details. It's a bit messed up here. We don't worry about that. But then you have what you get at the end is actually your I. Remember, that's the real component of your symbol, A, lowercase a, not the same as big A. And then you have your Q. And they come out at the end here. And you have I multiplied by a cosine minus Q multiplied by a sine of the same frequency. Aha. So that is what happens. That's how you modulate your carrier. You actually somehow have to split it into the sine versions. You have to like phase shift it, which I'll get to. And then you have to just multiply them with the real and imaginary parts, and then add them, invert the imaginary version, but that's okay. You just kind of basically just adding them, right? So this is what this block here to the right is called an IQ modulator, and this is depicting exactly what I just said. Oh, sorry about that. I don't know what that was. Yeah, so this is depicting what I just said. So we have ignore some of these blocks. This is a bad picture. Ignore these and these and these. Just imagine you have at the top here your I and your Q at the bottom. So the I and the Q. So what we said here is that the result, S of t, is, let's go back a slide, is I times a cosine. Let's see if we have that. So I at the top branch. And then on the right here, we have a mixer, which is another way of saying multiply, times the cosine. And then we're getting that. And then on the left, we have minus Q times sine. We have a Q coming in at the bottom, and then we have minus sine being multiplied. And then at the end, we have an adder, which is what we have. So this is how you make, it's called an IQ modulator, but it's basically a digital modulator. An IQ modulator is the name for the hardware implementation. So anyway, the point is here that, well, we don't see a phase modulator. That's great. All we have is multiplication. And that's just amplitude modulation. These are all very simple hardware blocks, like multipliers, adders. I know we have our carrier being the cosine is the convention. And then you have this minus sign. You might be like, how do you get that? Well, you can literally just make, first of all, multiply by -1 block, boom, minus cosine. Or I guess you do that after. But then you can also just like create a fixed phase shift block that shifts it by 90 degrees to get minus sine or whatever. I don't remember the exact phase shift you could do to get from cosine to minus sine. But the point is that you could design it once and then it's fixed. It's forever. And I know I said that we don't like phase modulators, but we don't like variable phase modulators. We like fixed ones. Those are easy. You make them once, you never have to worry about them. So these are all very simple blocks. So this is how you implement a digital modulator in hardware. So let's move on a bit to talk about some digital modulation schemes. These are going to be very important in the digital modulation communication space. When you look up stuff online, you'll run across these things, and you will run across some things called constellation diagrams. So let me just give you some intuition of where that word comes from. So think of looking up in the sky at night and you see a bunch of stars, and that makes a constellation. So these things were called constellation diagrams because their patterns look a bit like they've got some patterns of stars, that you got these points and you can draw lines between them in the same way you do with star patterns. So that's what we have here, the constellation diagrams. And we have a few different ones. So the key thing to remember is whenever you're thinking about theory, switch to polar form, okay? Don't think about IQ rectangular form. Don't think about it. You'll get confused. So let's look at the first one, this OOK thing. It's called on-off keying. I think we covered this before. But what we have here is, okay, thinking in polar form, we have two complex numbers, same phase, 0 degrees. Remember, that's distant angle from the x-axis, real axis. And then they have different magnitudes, different amplitudes, right? So this is what on-off keying is representing. QPSK, what do we have in polar form? Well, they're all the same magnitude, and they have different phases. So this is what's going to happen to the carrier. They're kind of telling you this. This is what these diagrams tell you, what they're going to do to the carrier. Here we have QAM. This is for QAM. This is actually a bad example because it has the same magnitude. This is actually equivalent to this. It's a special case. I'll cover QAM on the next slide, I believe. And then PAM, don't worry about that either. It's okay. That's just like amplitude shift keying is another word for that. Is when you have many amplitudes. And on-off keying is the trivial case of amplitude shift keying when you just have two, on or off, right? So here's what I said I was going to cover. So QAM grid. QAM is a very important one. It's what's used most of the time. I think Wi-Fi uses QAM. No, Wi-Fi uses OFDM, but don't worry about that. But I think within each subcarrier it uses QAM, maybe. I don't know, but I'm pretty sure it's using Wi-Fi. But I need to check my facts. But so the point here is, it looks like a grid. You've got like these rectangular patterns. You know, just like a rectangle that goes out and out and out. And if you think about it in polar form, well, let's look at 8 QAM. So we have our point. Actually, I'll look at yeah, sure. 8 works. It's a bit small for me, but it's fine. So we see the first ones here. We see that these 4 will have the same magnitude, but these ones will have different ones than that, and these will have a way bigger magnitude. So with QAM, it's the most general type of modulation where you're varying both the amplitude and the carrier. You're varying. No, wait. Well, sorry. You're varying the amplitude and the phase. Okay, you're varying both of those two things, and that's what's reflected in these diagrams, because they're all at different angles from the x-axis. They're not all in a straight line. So they have different phases and they're at different distances. So varies both of those two things, right? Okay, so that's what we have, and then what we see is that the naming convention, 6 QAM, 8 QAM, the number in front being how many points you have in the grid, 12, 16, 24, 32, 48, 64, and this goes all the way up to 256 QAM, which is crazy, but it can go. Actually, it might even go higher than that nowadays. Like you can get such a big grid with so many different combinations of carrier amplitude and phase alterations that it's crazy. But yeah, that's the idea here. And then to end this lecture, I just wanted to talk a bit about some terms that you're going to see: bit error rate and symbol error rate, denoted BER and SER. BER is a very important term. So far, I've shown you constellation diagrams where they're all very neat and tidy, and that's more on the transmitter end, because these are what's going to send. But if you send a cosine wave and of a certain amplitude and phase, and someone walks in front of the transmitter and then blocks it, you're going to lose. It's going to attenuate it, and you're going to lose some amplitude. So the receiver is going to receive a cosine with a much smaller amplitude than it was expecting, right? Than it was transmitted, I guess. And then it's going to receive maybe that's going to shift the point. If you're considering amplitude shift keying where they're all on a line, it's going to shift it way down, and now you're going to essentially receive the wrong symbol, because the way this works is you pick the closest one at the receiver. That's what the receiver does. So it will take the complex number it saw, and it'll go, okay, I know the constellation is 4 QAM. I'm going to pick the closest point that it most likely was. Okay, yeah, it's that one, and it might get it wrong, and these are decision errors. So when you make a decision error on a symbol, it's called a symbol error rate. The symbol error, it's called. And the symbol error rate, SER, is the rate of you making the wrong decision. And it's like per second, because these things run over time. So they make a lot of mistakes over time. So it's like you make let's say it's like 0.25, which would be really bad, but it makes a mistake every 4th symbol. Then you have bit error rate and bit errors. And because bits map to symbols, whenever you have a symbol error, you are going to have a bit error. Like, that's going to happen. The thing is, the bit error rate can be the same as the symbol error rate or larger, and the details of that I'll leave to you guys to figure out later on and investigate on your own as you learn about the stuff. But the point is, they're different notions, but they are connected. So if you make a symbol error mistake, symbol error, because bits, let's say 0, 0 maps to a certain symbol, and now you guess the other one, which is 1, 1. Now you're making 2 bit errors, but you only made 1 symbol error. So you can see why there can be different numbers, but the patterns are similar. They occur in the same times. Yeah. So the only thing I've left to kind of cover is an important trade-off I want you guys to remember. Everything in engineering is trade-offs, and communications is like the truest, most pure form of that. Like, I think it shows that so many times. There's so many trade-offs, and it's so important to remember. So there's no free lunch is the classic expression. So what is the trade-off here? It's that if you use a denser grid for your constellation, in the sense that you use a higher order modulation scheme, is what it's called, which would mean that you're sending more bits per symbol. Like, let's go to 264 QAM. So there's all these possibilities, all these different combinations, and we can map now more bit patterns to each one. Like 111001 is the most top left of the 64 grid. you know, because there's 64 different combinations. Now long bit patterns can be sent over the same fixed time interval. And that means you have, you know, faster data rate, faster bit rate. You have a faster, and that ultimately means you have a faster speed of transmission of communication, which is great. But the trade-off here is that if you have bad conditions, like high noise, a lot of interference, and you make a lot of symbol errors, then the higher order modulation scheme you have, the worse it is. Like if you have a very low order, it's okay if you like have a bit of noise, because it's still gonna be like it has to be a lot of noise for it to be like way over to a different modulation, like a symbol, if the modulation scheme order is low. Like if you look at the QPSK, they have to literally, if you add a symbol, let's say this green one's like the received one, if it's anywhere in this entire quadrant, you're going to guess the right symbol. So it has to be a pretty big mistake for it to be, you know, all the way in a different quadrant. Whereas 64 QAM, even a little bit of a movement within the same quadrant, you're going to guess a different symbol. So that's the problem. It makes making mistakes more likely. So just something to keep in mind. I'll leave this there. I will just explain one last thing for you, because that was a lot of words and a lot of theory. Here's an interesting takeaway for you, and it's that your phone actually does this and utilizes this principle without you even knowing. If you are close to your Wi-Fi router, you'll notice fast speeds. But if you go really far away from the router and even go like outside, you'll notice that the Wi-Fi speed drops dramatically. Now, the reason for this is your phone and the router are working together, and the router is going to notice that you're far away, and it's going to switch to a lower order modulation scheme. Like, let's say it's originally had 64 QAM when you're really close to the router, so it was lots of bits per the same interval, so high data rate, very fast speeds, and then you went really far away and it switched to on-off keying, let's say, like in the most dramatic sense. So you only sending in the same interval now a 1 or a 0, so 1 bit, as opposed to, let's say you were sending like, my brain isn't working. Let's say you were sending like 50 bits per, maybe it's 64. I don't know. Bear with me. But let's say you're sending 64 bits the same interval, and now you're sending 1. So your speed is gonna drop dramatically, and that's why, you know, like the Wi-Fi speed gets so bad when you're far from the router, because it's literally picking a lower order modulation scheme because it doesn't want to make mistakes. That's something that I learned that was really interesting, is that the router will prefer you have lower speed than no connection at all, which is kind of obvious if you think about it. Like, it wants you to be able to communicate at all. It doesn't care about like a certain speed. So it's going to gracefully decrease the modulation scheme order so you can still communicate as the performance of the environment gets worse. So anyway, that didn't make sense. Don't worry about it. It was just something I thought was cool. So yeah, that's all I have for this lecture. This was just an intro to digital communications. I'm sorry about the fragmented online hybrid in-person thing. I'll hopefully have that fixed for the next one. But yeah, so next time we're going to cover pulse shaping, which is a very important topic within digital communications. And yeah, hope you enjoyed.